Hello everyone, good morning and good evening. My name is Shubha and I am a researcher at CellStrat. And today we will be looking at parameterized efficient fine-tuning of large language models. So in this, we will be looking at one particular technique called as LORA. So some of the topics that we plan to cover in the next 1.5 hours will be, we will look at how LLMs are fine-tuned. So fine-tuning within LLMs, we will look at some of the evaluation metrics. And then we will have to understand the disadvantages of full fine-tuning in LLMs, so that we jump into our main topic of today, which is parameter efficient fine-tuning. So there are different methods different methods that can be used to perform PEFT, and we will be looking at one of the methods, which is LORA. And once we understand the theory behind how LORA works, we can see how you can use any of the data sets to implement parameter efficient fine-tuning on that particular data set by picking some LLM that we can, and we will have a detailed code walkthrough. So this is what I plan to cover today. At any point in time, any questions, so just please feel free to post it on chat or feel free to pause and ask at any given point in time. So we all, let's get started over here. We all understand that large language models generally have a huge set of parameters, and they are pre-trained on a very large corpus of data, very large corpus of data that is available in public. So in case you want to use any of these large language models on your own data set that is private and confidential to any particular organization, you try to perform any of the NLP tasks on this data using the large language model that you are using, it will not be able to give you accurate results because it has not seen the data that you are using in your organization. So what you have to do in such a scenario is, we will do what is called as a full fine-tuning. We will do what is called as a full fine-tuning over here. So you have your pre-trained LLM, a huge LLM that is trained on corpus of data that is publicly available, and you want it to work for your own internal data. You will have to do what is called as full fine-tuning. And how do you do full fine-tuning? So it is basically a supervised learning process where you have the input and the output, just like our normal machine learning algorithms. You have your input. If you're trying to do a sentiment analysis, you have your sentences and you have the sentiment at the end, whether it's positive, negative, neutral. So this kind of supervised learning data set is what you pass into your already pre-trained LLM, and all of the weights of this LLM will be updated, and this is called as full fine-tuning. Before trying out full fine-tuning, what you can do is you can try zero shot or one shot or few shot inferences. So one shot or few shot inferences is something that you pass some instructions when you are asking the question itself to your LLM. So let's say you're trying to ask a question to summarize a kind of huge conversation. You pass the instruction to it saying, summarize the below input that you are trying to provide. This is called as instruction prompt, and this, if you are just giving your instruction, it will be called as a zero shot. If you give one example, it will be called as one shot, and if you give a few examples, it will be called a few shot inference. So you give few examples, like I have this paragraph A, and this is the summary of paragraph A. I have paragraph B, and this is the summary of paragraph C. Now I'm going to give you paragraph C. So what is the summary of paragraph C? So if you're asking something like this, then it will be few shot inference, and you can do one shot or few shot inference even before trying to full fine-tune your LLM. And if it does not work, then what you do is you try to do a full fine-tune LLM. And full fine-tune, the sentence is told, the definition is told over here. It is just like a supervised learning process where you use the data set, like the input as well as the output, and you fine-tune this LLM to update all of its weights. So we have now understood what is full fine-tuning and what is one-shot and few-shot inference. What is instruction fine-tuning? Instruction fine-tuning is when your input data set contains the instruction as well. So if I add an instruction over here, the below tasks will summarize the input, and if I give an input and if I give a summary, then that is called as instruction fine-tuning. You can instruction fine-tune a given LLM for multiple tasks. Like I can say, I can give 100 examples for which explicitly gives the instruction of summarizing in 100 examples for language translation and 100 examples for sentiment analysis. So you can instruct fine-tune your LLM for multiple tasks. As it is shown over here. So this is what is your pre-trained LLM that you have, and there are different tasks that you have, like you want to summarize or you want to rate a review or you are trying to translate and all those things. And you can instruction fine-tune your LLM on all of these tasks. So let us try to understand what are the let us try to understand what are the disadvantages of fine-tuning. Now, LLMs generally have huge parameters. So like GPT-3 has around 175 billion parameters. And fine-tuning any LLM would mean that all of the parameters that are there in the LLM will be retuned. And it also results in one more disadvantage, which is called as catastrophic forgetting. So basically, an LLM was pre-trained with some particular tasks, with some particular data. And if you are fine-tuning it on huge data sets, on multiple tasks, it can significantly increase the performance of the model on that particular task, but it can lead to reduction in its performance on the other tasks that it was previously trained on. So this concept is called as catastrophic forgetting. And you may also have to, if you want your LLM to perform on multiple different tasks, you may have to fine-tune it on all of the different tasks at the same time. And when you do it, like you will be retraining or fine-tuning all of the weights within your LLM, which requires very huge amount of compute and storage. And it will be like, especially if you pick models like GPT-3 or really huge models, their parameters goes all the way somewhere to 175 billion, and it is a huge problem for compute and storage. Once this is done, you will have an instruct fine-tuned LLM. So I will pause here for a minute. If you have any questions, we can take the next week.
No, so all the weights are adjusted. I mean, how can all weights be adjusted of LLM?
When you are doing a full fine-tuning, all of the weights will be adjusted. You will
no, but the LLM is GPT. It's an OpenAI environment. So the model is residing in OpenAI environment, let's say.
You will have to download the model on, if you're trying to tune it on SageMaker or something, you will have to download it on your SageMaker, and full fine-tuning, you need that amount of space and compute.
No, but that would be for downloadable LLMs like Llama. But for API-based LLMs such as GPT, which is not downloadable, it's in OpenAI cloud.
So yes, I mean, I gave GPT as an example so that you will have to signify the amount of parameters that you have. But if you are having a huge parameter LLM, then all of its weights will be pre-trained, all of its weights will be fine-tuned or changed if you are doing a full fine-tuning.
I still don't get it. So GPT LLM is residing in OpenAI cloud. So are you saying you are intercepting the weights of that model in OpenAI cloud?
No. Okay. Just a clarification over here, Vivek. I have not done a full fine tuning on GPT, or I'm not pretty sure on how that works. But I gave it as an example to say that a huge number of parameters. In case you pick some huge LLM like that, I'm trying to tell you that that will be the magnitude of the parameters that you will have to fine tune. So I have to really relook into if you can fine tune GPT, I have to really relook into it. But if you in general take a downloadable LLM with huge, you have to retrain all of the huge parameters.
Got it. Got it.
Okay, thank you. Shall we move ahead? Any other questions? Let us quickly look into some of the evaluation metrics. Let us try to understand some evaluation metrics of how to evaluate these LLMs, and then we will look into the different methods of parameter efficient fine-tuning. There are two main scores that you can use for sequence-to-sequence models. The rouge score is generally used for text summarization, and the blue score is used for text translation. So in both of these cases, you will be comparing it with the human-generated summary or the human-generated translation to understand how well your model is performing. So the formula for rouge 1 is really very simple. You calculate rouge 1 recall, rouge 1 precision, and F1 score. So to calculate the recall, it will be the unigram matches divided by the unigram sin reference. And for the precision, it will be unigram matches divided by the unigram sin output. So over here, here is the reference and here is the output. So all of the unigrams and the references matching with the generated output. So that will be 4, and the number of unigrams on the output will be 4. So recall is giving you a high score, but if you are, you can also use precision, and a better score will be the F1 score. And you can go on with this way, like you can calculate rouge 2 or rouge 3 by instead of using unigrams, you can use bigrams or n-grams to kind of try to understand how it works. But one more common metric is to calculate the lowest common subsequence. So if you try to use the lowest common subsequence, you will get what is called as the rouge L. So the lowest common subsequence will be either it is or cold outside. So it will be, the number will be a 2, and you will use that with along with the unigrams in reference or unigrams in output, and these are the scores that you will get by using LCS on rouge. Apart from this, there are other variants of rouge. Like as I told, you can use bigrams or n-grams that can be added with rouge, or there is also a clip function. So if for example the word cold is used multiple times, maybe in the output, like it is very cold outside, it is very cold outside. So if you're having something like that, then what you can do is you can use a clip function. If any particular word is occurring multiple times, you can do a clip to just flip to 1 and add to your rouge score. There are slightly different variants on the rouge score, but in general, this is the formula that is available, and it is generally used for summarization tasks. So now we understood the disadvantages of full fine tuning, and we will have to see what can parameter efficient fine tuning do to mitigate the disadvantages that we are having. Any questions here? Okay. So it is not just the weights that we have that gets when you are doing a full fine tuning, it's not just the weights which store memory. It's also other things like your gradients or optimizer states or your forward activations. There are lots of other things apart from your weights which needs to be stored in your memory. So this will go up to 4 to 20 times the number of weights that you have. So if you are having a huge set of weights, that is only the weights that you are calculating. In full fine tuning, apart from your weights, there are other parameters which will also occupy memory. And as it is, the weights of the LLM itself is very huge. So the weights of the LLM itself is very huge, and on top of that, all of the other components of your neural network architecture is again going to take even more space on your disk. So the PEFT. So what PEFT does is we are only going to update a very small set of parameters, and it is less prone to your catastrophic forgetting problem of full fine tuning. So whatever set of weights or parameters you have, it's only picking up a very small subset of those parameters and fine tune only those subset of parameters will be your parameter efficient fine tuning. So on the next slide, we will see different methods of PEFT, and we will look at one particular approach on how this can be done. So you select a subset of your initial LLM to fine tune. So if you look at any LLM, it generally follows the transformer architecture. So in your transformer architecture, you have your encoder and decoder, and your encoder or decoder will have a self-attention layer as well as a feed-forward neural network. So most of your trainable parameters will be in the self-attention layer. So what you do is you can select a subset of your self-attention component to fine-tune your LLM. There are different methods to do that. Or there are also different methods to select, like if you want to choose the self-attention component of your architecture or the feed-forward part of your architecture or a combination of both, you can do that. But the selective method basically is to select only a subset of those parameters and fine-tune it. And reparameterization, here is where LORA falls into this category. So what you do is you create a low rank representation or lower rank decomposition matrix, and you just fine tune the weights of that particular matrix. And then once it is done, you add it to the original weights, and then that whole thing after adding it to the original weights can be used for your inference. So most of the weights of your neural network will be frozen, and you will create a low rank representation, and only this low rank representation matrix is the only thing that will be tuned, and then it will be added to the original frozen weights, and this whole thing can be used for inference. So if that was just an overview of what LORA is and what I told just now, but then we are going to go through that in detail with examples and the architectural diagrams. The third method is the additive method, where you add more trainable layers to the parameters of your model. So you already have your existing trainable parameters. You can add a few more trainable layers to your model, and that becomes your additive approach of PEFT method. So PEFT can be performed with, PEFT is basically, we are trying to reduce the training of all of the weights of your LLM. Instead, just take a part of it, a subset of it, or add a few more layers and few more weights to it, and only fine tune those weights, whereas a majority part of the weights of your architecture will be frozen. So if you are trying to implement something like this is in general called as parameter efficient fine tuning. And there are many different approaches and many different algorithms that can be used. And today we will be looking at one of them. So I have picked this up from deeplearning.ai. So here is your encoder architecture. your input will be coming here. It will be embedded. It will be converted into embedding vectors, and it will be passed into your encoding architecture. So this left component of it is your original LLM weights, and most of these weights will be frozen. And then you will inject two rank decomposition matrices. So basically, your rank decomposition matrices are similar to factorization or something like that we have seen in recommendation engine. So if your original weights are of the dimension A cross B, what you can do is you will pick up a very low rank number, and so this will be B and this will be A. You will form two very small low rank matrices, and once you multiply these two things, you will be getting the huge matrix A cross B. And this A cross B will be of the same dimension as your original frozen weights, and it can be added together before inference. So this left part of it will be the frozen weight. This right part of it is formed by just using very small low rank matrices, which will be trained. You can train it for different tasks, like you can train it for summarization or sentiment analysis or whatever. And you will get your low rank matrix. You will get your matrix, which is of the same dimension as your original matrix, that is going to be added and which will be used for inference. Pausing here for a few seconds. Any questions, please let me know.
So low rank, does it mean like low values?
No, it does not mean low value. It means that you are taking the most important parameters of your original weights. So if you have understood what is rank decomposition matrices, or how do you create it, singular value decomposition, what they generally do is they create two matrices where the dimension of your columns will be the same and dimension of your row will be the same. So you just give me a minute. So let us say that you have one M cross N matrix. Okay, what you can choose are, let us say M and N are very huge numbers, maybe some 50 by 80 or something like that. You can choose a very small rank, maybe R is 1 or 2. Then what will happen is you can do something like M cross 1 and you will do something like 1 cross N. You will create two low rank matrices like M cross 1 and 1 cross N. And when you multiply these two matrices, you will get back the original size of M cross N. So R can be 1 or 2 or 4. It can be very small, where since it is very small, this will just be a columnar matrix, and this will just be a row matrix, and this will just be a columnar matrix. So this is your rank, and you will create two smaller matrices using this rank. And once you multiply these two, A and B, so that is what they are trying to show between B and A over here. B is your columnar matrix, which is having all the columns, but it is very small, and A is your row matrix, which is having all the rows, but it is having only one column or very small. And when you multiply B cross A, you're going to get something of the full dimension. Like if you multiply M cross 1 and into 1 cross N dimension, you will get M cross N dimension.
There's some more question on the chat, I think.
Shubha Bhavin here.
Hi.
So I had put one of the questions on chat. So my question is, can PEFT be applied on both the API-based GPTs and downloadable GPTs, like all the three methods?
I'm not sure on GPT. I will have to. I will check this out and I will let you know, Bhavin.
Thank you.
Yes. So one more question over here is, does the algorithm automatically decide which parameters to fine tune and which one it drops? So we will look at it in the code, but yes, there are actually, the thing is, you have APIs and libraries to perform all of these tasks. Yes, the algorithm itself picks up what are the parameters to fine tune. All the hyperparameter that you get to play around with is the rank. So you can try out for different ranks, like rank 1, 2, 4, 8, and so on, all the way till 64 you can try. But then using that particular rank, the decomposition matrices will be formed by the API library itself. We do not have any, we cannot modify that code. Rank is a hyperparameter that you can choose. So you can look at the evaluation on how different ranks are giving you better scores or not. So we will see towards the end, there is a screenshot that I have put from the paper, LORA paper itself, where after rank 4 or something, it starts to plateau. There is no significant decrease in loss. So you can kind of settle at that particular rank, and even after moving higher also, the loss kind of does not decrease. So it is kind of a trade-off between whether that you want that very small accuracy or you're good with the low parameters, because if rank is low, your parameters are also significantly low. So what is the advantage of this matrix decomposition is, I will try to tell this at a very high level. Basically what happens is, you will try to find out the rank of a matrix by calculating its determinant value. If the determinant is not equal to, by using the determinant value, you will try to calculate the rank of a matrix. And using, you can generally, if you are having linearly independent rows or columns, the rank of the matrix will be equal to the dimension of your matrix. Like it will be either equal to the row or the column. But if there are not linearly independent rows or columns, the rank will be subsequently low. So it is generally used, like if you are having very sparse matrices, you use the decomposition in order to reduce the sparse matrix into a, because a very sparse matrix is going to occupy a lot of space. You generally use decomposition to reduce that sparse matrix into compact one, where it carries all the essence of your sparse matrix, and it is really very compact, and it does not occupy a lot of space. So is the low rank matrix a matrix with smaller dimension? Yes, it is a matrix with smaller dimension that is somehow captures only the essence. As I told, the bigger matrix will generally be a sparse matrix. So examples for this will be, if you are trying to store all of the vocabulary in a dictionary. So let us say all of the words in the vocabulary is your corpus, and you're having a document. So document, let us say there are 1,000 words in the vocabulary, and document 1 is only using some 10 words or 20 words, and document 2 is just using some 15 words or something. So yes, single value decomposition matrix. So when this happens, it is if you are trying to put all of the words in the vocabulary on the columns and all of the documents, then you get a very huge matrix, and it is a very huge matrix with very little data, which is very sparse. So you use this technique of SVD to bring it into a smaller weight, bring it into smaller dimension, and only fine tune the most essential part of it. And it is divided in such a way that it is divided in such a way that you use this R over here. R is a tunable parameter, and once you multiply, you will be able to get, when you multiply both of them, you will get the size of the original matrix, which can be added to your frozen weights. Shall we move on? The same thing I have got it from the LORA paper. There is this LORA paper. I will share the link. This is what was explained on the paper. Let us consider any model, any task learner, which is represented by P5 of y comma x, where y is your output and x is your input. So you will have several downstream tasks. So your downstream tasks can be, you are giving a plain English query, which has to be converted into an SQL query, or you are giving a summarization or whatever, where your context and target pairs will be z, x, y, comma, yi, where x, y is your input and yi is your output. So during full fine tuning, what happens is the model is initialized to the pre-trained weights phi naught, and later on it is updated phi naught plus delta phi repeatedly by following the gradient to maximize your objective. So this is our general deep learning principle. You have your weights phi naught, which is updated repeatedly with delta, which is updated repeatedly with delta phi. And your objective will be to maximize log of your model y comma x, where it is less than t. So this is your general deep learning principle. So the drawback is you will have several downstream tasks. So for any of the downstream tasks that you can choose, maybe SQL conversion, you will have to learn a different set of parameters, delta phi, where the dimension of delta phi is equal to phi naught. And if you are trying to use it for another downstream task, so now you did an English to SQL translation. If you are trying to use it for another downstream task, then you will have to store another set of weights. So they are using a concept of parameter efficient. Sorry, I'm not able to get this pointer. I'm not able to see this pointer. Okay, yeah. So you'll use some kind of parameter efficient approach over here, where you will try to say that the delta of phi that you are trying to do is only using a small set of parameters theta. So what will happen is you will have to update P phi of delta of phi, where it is only where you will be only updating a small set of parameters which is given by theta, and this becomes your overall objective function.
No, I didn't understand. So what changed from before, from the previous slide, the equation?
Yeah, so here this, okay, just give me 1 minute.
This is maximum likelihood estimation in
Look at this.
regression.
Here you are trying to use, if P phi is your original model that is told over here. See,
Right.
P phi y of x is your original model, and here you are trying to update every parameter within phi naught. And in the next one, you are telling P phi plus delta phi of theta, where theta is a subset of parameters. Your delta phi, or whatever incremental weight that you are trying to add, is not all of the weights, but it is a small subset which we are representing by theta. So this set of weights will be frozen, and this delta set of weights, which is a small subset represented by theta, is what will be fine-tuned, and that will be added to your frozen weights, and this entire thing will be used for inference.
But how will, okay, this is fine. How will you ensure that this delta phi can represent different tasks and not just one specific task like text summarization alone?
Yeah, so what, since this theta is a really small value, so generally as per the paper and as per other things, it'll be 1 to 2% of your original weights. So what you can do is, I have another figure. I will just jump to that so that you over here. I have picked this up again from deep learning AI so that you understand. So what you can do is you can train different rank decomposition matrices for different tasks, and you can update the weights before inference. So now let us assume this is task A, which is represented in orange. So you create two smaller matrices which are represented by these bars. And you multiply, you will get a huge matrix. This is added to your frozen weights. This is your frozen weights. This is task A. Let us assume you have another task B, maybe summarization or something different. For task B, again, you only have to fine tune a very small subset. And when you multiply, you will get the bigger matrix. And you can add it to your original weights. So over here, you can store both of these things, both of this and this and this and this and this in your system, because it is having very small, it consumes very small memory. So during inference, what you can do is, for this frozen weights, you can add yellow over here, which will be for summarization tasks, and you can easily switch it. So APIs and libraries are available for us to easily switch. You can easily switch it to use green over here, where it can be used to perform task 2.
Oh, at runtime you change which set of differential
Correct.
weights you use.
Correct.
Okay.
So initially, while training, if you are having 5 tasks, since the smaller matrices that you're having does not consume a lot of time and compute and space, you can fine tune it for 5 different tasks and store it on your system. And during inference, it can be switched. So over here, you can see that during inference, they are adding it with yellow, and over here during inference, they're adding it with green.
So fine tuning becomes very task specific only. So okay, so it's not artificial general intelligence. It's very task centric.
Yes.
Okay. Yeah, it's clear.
Okay.
So
Yeah.
we cannot create a generalized AI system with fine tuning. We have to keep it task centric.
Correct.
Hi Shubha, this is Vikas
Yeah.
here. So like for each of the tasks, would there be a separate output model or no? It's just the same model in which and dynamically at runtime for runtime inference it would be just using that appropriate task.
Yeah, so you can if you pick up one LLM model and decide that I will use this LLM model for all my tasks in my organization, then you can use that LLM model, fine tune it for 5 different tasks, and whichever task is being asked on inference, you can just shift the weights and you can do it. Or if you decide that for 3 tasks you will use one LLM and for 2 other tasks you will use a different LLM, different model, that is also an option.
Okay. Thank you.
Yeah, Shubha, I have.
Yeah, sure.
So let's say there are like 4 tasks,
Mhm.
and for each task we are kind of maintaining different, like let's say those low rank matrices. But let's say like if we just combined, maybe let's say increase the rank and multiply by 4. So for example, let's say instead of let's say using m into 1, if we use like m into 4, and then it on all the 4 tasks, like simultaneously, like will it be able to
No, I think by increasing the rank to 4, you will not be able to do it on different tasks. It really depends on your training data set. So if you look at this first thing, you are giving Z. Z is XY comma YI over here. So XY is plain English text, YI is the SQL query that was generated. So if you take 100 such examples, 100 examples of plain English query and the corresponding SQL query that was generated, you can train it on the SQL task. So the Z will increase. Like if you want to do English to SQL conversion and summarization also and sentiment analysis, the Z will increase. You'll have 100, 100, 100. So instead of that, what you can do is, as I showed in the other figure, what you can do is you can take the initial weights, create a low rank matrix, fine tune it for that particular task, and switch it in inference time.
Okay, but let's say in full fine tuning, when we do, let's say in order to avoid that catastrophic forgetting, so we kind of like train on multiple tasks simultaneously?
Yes, that is possible. But the
Okay.
advantage of PEFT on full fine tuning is, if you are doing full fine tuning on, or you can do for multiple tasks simultaneously in full fine tuning, but the compute and time and space it will be really very huge. And this is like significantly lower. It will be like less than 5% of your whole trainable weights.
Okay.
And with a very low trade-off in accuracy. So let's say with full fine tuning, definitely full fine tuning will be of higher accuracy compared to PEFT. So let's say with full fine tuning, you get a 70% accuracy. Maybe with PEFT, you will get a 65% accuracy. So that is the trade-off. If you really are looking at that accuracy, you may still have to put with full fine tuning, but it is like huge compute and huge memory.
Could we run into underfitting and overfitting problems?
Correct. So something like that, where it is a trade-off between, but if you considerably we will look at it in the results, some of the results that they have published on the paper. But if you really look at, and also in our code, if you look at the results, it is not that significant, and given the amount of savings, it is worth the trade-off.
Okay.
So one question. So we have some specialized models for specific tasks, such as, let's say, text to SQL, such as NSQL and DFOG AI models, right? Those are the models which have been created by such adapters on specific SQL examples on the generic LLMs, or how is it?
I'm not sure on that. I'll have to get back. So I think they would have done, if you're talking about those kind of models, it will be done with full fine tuning or full pre-trained. This PEFT will come when you want to use a pre-trained model, when you want to fine tune on top of a pre-trained model. But if you're talking about the existing original training of your LLMs, I think it is done on the full data set by tuning all of the weights. So.
Okay. Secondly, we do PEFT only when we don't have a task which has been trained on the original LLM, right? Not on the data.
It is both task as well as data. So a lot of organizations' data will be confidential, right? It will not be available on public. If you take any LLM for that example, it can be only trained on what is available. What is within my own organization is never leaked outside. So let us say some kind of contract papers between customers and your vendors, or between you and your customers, which has real sensitive data between what was your transaction, and all those things are not available outside. And if you want to kind of summarize, you have a huge PDF document which you really want to summarize, then if whatever you do, you have your own document, you can't go with GPT or something like that and try to ask the summary of your own paper. You will not be able to get accurate results. So you have some such contract documents or manuals which are very confidential and internal, and you want to do it on the data. So yeah, both, it is like both. So if you want to tune it on data, or if there is some particular task also, maybe which the LLM has not seen, even then.
Got it. Okay.
So repeating this once again, I have picked this sentence as it is from the paper. So it is further encoded into a smaller size set of parameters theta, where dimension of theta is equal to dimension of phi naught. Phi naught is your initial set of weights. So that is the reason they're able to add both of it. And how is dimension of theta same as dimension of phi naught? That we saw. If I say m into 1, and then I say 1 into n. So when you multiply these two things, you will get m into n, which will be same as the dimension of your phi naught. And so your delta of phi is nothing but delta of phi, where only you're trying to find out theta. And so it becomes like significantly lower. And the difference between this equation and the next is, in full fine tuning, you're using the full model over here, but here the whatever I have circled is all frozen, and this is the only thing that will be tuned. And add these two, and you're trying to maximize the objective. So again, this is the same, but it's just explained in a different way. And this is again taken from the paper itself. So you have your pre-trained weight matrix W0, which belongs to real numbers of the dimension D, K, D star K. So D star K is the original dimension of your weight matrix. So you are trying to calculate W0 plus delta W, or delta W is given by DA. So this is your pre-trained weights, and here you have your A and you have your B, and R is the rank, which is your hyperparameter. So your rank R will generally be the minimum of D, K. So if you're having D, K, it will be the minimum and it will be less than the minimum. So it has to be less than the minimum, and it is generally a very small value. So the output that you get over here is in X is your input. So X into W0 plus delta W into X, or instead of this delta W is nothing but your B cross A. Those are the two rank decomposition matrices that you have. Any questions here? So again, one more slide from deeplearning.ai. So the origin, they have chosen the original transformer model representation where D, K is 512 by 64 for each set of weights. So this was the dimension that was used in the Attention is All You Need paper from 2017, and it has around 32,768 trainable parameters, 512 and 64. So if you break it, if you choose a rank is equal to 8, so R into K is going to be 8 into 64, and D into R will be 512 into 8, and you will get an 86% reduction in your number of parameters. So instead of 32,768, you will just get somewhere around 4,096 trainable parameters. But even over here, R is kind of slightly high. You can reduce R to 4 or even to 2 and test it out to see how it performs, and if needed, you can try to increase the weights of R, the rank of R.
Yeah, I remember we used to do this in classic deep learning also for network compression. So because an m into n could be broken into m into 1 and 1 into n. So there were vector techniques or matrix techniques to decompress a large neural network. So it was a similar concept which has been seen before in DL.
So this is something that I wanted to explain, but we already covered. So basically, you can use the same thing for multiple tasks, and it is easier for you to. All that you have to do is only store the updated weights. So whatever is in this orange is what you have to store, and you don't even have to store. You just have to store this row matrix and column matrix, and you have to just store the row matrix and column matrix, and then you just multiply, and you'll get the huge matrix which will be added to the frozen weights. Any questions here?
So Shubha, have we done this at our workplace or something?
I have not done this yet. I just picked it from Coursera's example.
Okay.
But no, this I have not done this at workplace.
Because I'm yet to come across a commercial, situation where a fine tuning was done in a client project. At least in my project or discussion, every time we settle with RAG based, semantic search method, fine tuning has not come up, or we are always afraid of fine tuning because it is more complex, right? So we tend to settle with RAG typically.
Correct. Probably at least for a POC sake, it can be done to compare the results. So I remember that Bhavesh was once suggesting this, that you can do a fine tuning, maybe if not a full fine tuning, something like this, and a RAG, and then compare the results to see at least how the two things are performing with respect to each other. So that is something that can be tried out. If not implemented in production, at least a POC kind of thing, just for understanding of the end results or the end score comparisons.
So we have been trying to create a productized, fine tuner in ImagineView as a general fine tuner which can suffix for multiple situations, but we have not seen an ability to do that. One of our LLM researchers has set up a custom fine tuning notebook, which you will probably also show, but he has said that it cannot be generalized as of yet in the ImagineView product. It has to be custom.
Okay.
Subha, I echo with Vivek. I would like to understand what could be the limitation of RAG where we need to go for fine tuning.
So RAG, actually earlier it was like there is a context with which you can send input to your LLM. But nowadays it's like the context is kind of really increased a lot. Earlier it was like just some tokens that you can send as input to your LLM. That was one of the limitations earlier. But then, I mean, at least for now, as of now, currently, that is the only limitation that I'm able to think.
I mean, the RAG is first level in context learning. So fine tuning is the ultimate, right? But fine tuning is harder. So we tend to try to make do with RAG.
Just to add what Shubha said, right? Just in myself, Vijay, I'm working with the open text. So if we see, right, most of our documents, it could be a technical documents or let's assume healthcare or the legal documents, right? The language is different. This whatever the current LLMs, right? They have been trained on the internet. Maybe they won't be able to reason out well on our particular language. When you say language, right, how we speak from the technical perspective or how we speak from the healthcare domain perspective. If we ask, be it like, I'm just talking about the open source LLMs, I'm not talking about the GPT-4, let's say Llama, the Mistral, right? If you pass, let's assume they haven't seen much of the healthcare domains or the legal domains. If you ask them, right, what it will try to do is it tries to generalize, like it will try to give in a generalized language, which doesn't fit, especially in the healthcare domain or the even in the technical domain where we are seeing. So, for example, let's say I take the example of like let's say Operations Bridge or the SMAX agent, where it will do a very specific task related to the technical documentation. Okay, you ask, okay, how to maybe let me give. Okay, you are asking about the PC BitLocker, okay, and it has to define in an certain steps or in a certain language. It should not generalize it. If it generalizes, right, it's gone. It has to taken in a step-by-step manner. These things can't be directly achievable using even in the RAG perspective, because the LLM capabilities, right? You have given the step-by-step approach, but they won't give in that the same format. They will try to generalize all the steps and compress it into, let's say, 200 tokens or the 500 tokens, which is not required or which should not be given to the end customer. That's where we have faced a similar problem. And when we have given a different sets of examples saying, okay, if the customer is asking about, let's say, installation, you have to give in a step-by-step format. If a customer is asking about, let's say, a ticket resolution or a ticket thing, you have to search and provide what's the status of the ticket or a Jira ticket, whatever. So when we have given this set of examples for the fine tuning, then the Llama model was able to understand what the customer is asking, and it is not generalizing as like previously what it used to do. So this is the difference which we have seen when we have done the fine tuning and without fine tuning.
Makes sense. Thanks, Vijay.
Thanks for this, Vijay. Makes sense. Okay, any other questions? So this is again from the paper. They tried to do it on GPT-2 medium using different ranks for one particular task. And as you can see, this was the different ranks that they did, and here is the value the loss values that are there, and different metrics were evaluated, but we can look at the rouge score or the blue score. And what has been highlighted over here is after 16, so you try to increase the rank and it kind of plateaus after 16. So after that, more or less, the loss kind of remained the same, and the scores also did not significantly increase. So at 1024, there was like, okay, it increased after that. So this was the best score that they were able to get. So it is kind of a hyperparameter that has to be tuned. And yes, so with very significant decrease, very insignificant decrease in loss or something like that, you can stick to lower ranks in order to get an optimal compute as well as an optimal score and value loss. So I have the code. Before we get into that, any questions?
But this is Ashutosh.
Yeah.
Now, I just wanted to know if there is any comparison. So there was a discussion going on between RAG and kind of fine tuning. Is there a some kind of comparison for a use case between how much compute and resources would be required in both the scenarios?
Yeah. So this example that I just showed, that they just, okay. So this was one example that they have taken from the attention all you need paper. So I have what is on the paper, but some real-time use case or something like that is what we have not done. Probably one such example during the code walkthrough, we can kind of see how many initial parameters are there and how many parameters will be fine-tuning with LORA or PEFT. But with attention all you need paper, each set of trainable weights parameters, each set of W was around 32,768, and by choosing a rank of 8, it kind of reduced to 4,096. So the code again I've picked it from deep learning.ai, but then we can go through the code walkthrough where for a dialog summary data set, there is a full fine tuning that has happened, and they have also printed the trainable parameters from a Flantify model. And by looking at the trainable parameters, and if you try to use LORA or some other PEFT method, you can also see how many parameters will be fine-tuned.
And is there a translation of this parameters number to say some kind of a dollar value?
So okay, I read it few days back, and not a lot of it is what I remember, but I will try to explain it at a high level. So convert parameters into dollar value will go something like this. You have what is called as, if you are trying to fine-tune a model, the number of parameters that you will have to see how many AWS instances do you have to take. I think the highest AWS instance that is there is that A100, which has got certain number of GPUs and certain number of GPUs and certain number of memory space that is there. And if these are the weights, you will also have to add additional components to it, like your gradient parameters and optimizers and state variables and all of those things. And this kind of converts into what is, I'm not able to get it on top of my mind, but the P flop or petabytes per flop or something like that. So how many one particular weight, how much of memory does it occupy? I think it occupies around 8 bytes or 16 bytes of data, one single weight. So if you're having something like 32,768, that will occupy that amount of data. So you will have to see, when you're trying to provision an EC2 system on AWS, you will have to see what is its capacity and how much memory can it store. And A100 is the highest EC2 instance that's available on AWS, and that is really very expensive. And probably if you are having very huge models, you will need quite a number of AWS instances, and you will have to look at the rates of those AWS instances on how much it costs for an hour, and then that translates into your dollar value. Pardon me, I kind of read this maybe 2 months or something before, and I don't remember the exact numbers on my mind, but that is how you try to convert these weights into dollars.
Okay, great. Thanks, Shubha. Thank you.
So I just try to explain at a higher level because I don't, as I told, I don't remember the numbers right on top of my head, but yeah.
That's okay. Thanks, Shubha. Thank you.
Okay, so my screen is visible, right? I will just make it slightly bigger. So our data set is a dialog summary data set, which we are getting from PyTorch. And there is this transformer or your Hugging Face library that you need to install and import. And you have your evaluate model. Evaluate model is used to calculate your Rouge score. You have your PEFT library. PEFT is used, you have your LORA lib where you can specify the LORA's configuration. Like mostly the rank is the main hyperparameter that you specify on the configuration. And PEFT is to convert using all of those configuration values, convert it into a model. So these are some of the libraries that needs to be installed and imported. So I have evaluate, and from transformers, the regular pre-training using transformers, using auto model for sequence to sequence LM. There is a tokenizer, and if you want to specify any configuration like epoch and batch size and all of those things, and you have your trainer to fully fine-tune your data set. So the data set was the dialog summary data set available on Hugging Face, and we will look at it. So it has a dialog, it has a summary, and it has a topic, and it has been divided into train, test, and validation data set with around 12,000, 1,500, and 500 on the validation set. And the model that's being used over here is your FLAN T5 model. FLAN T5 model from Hugging Face. So you specify your model name, and using your Hugging Face libraries, you load the model and you tokenize it. These are all simple code that you can get on your Hugging Face library and Hugging Face code as well. So over here is what we are interested in. This is a simple function that was written to get the number of trainable parameters from the model that we have loaded. And this huge number is the number of trainable parameters that the model that we have loaded that is the number. And when you say zero-shot inference, you do not give any example. You just specify a prompt telling, summarize the following conversation, and you just give a dialogue. That is all is your zero-shot inference. If you're having one-shot or few-shot inference, you just add couple of examples. You add one example or 4 or 5 examples for few-shot, and then you pass that as the prompt to tokenize it and get the output, and then Yeah, that is one shot or few shot inference, but this is zero shot inference over here. So now we are using the original model over here. Let me just scroll up and look at where is original model. Yeah, original model. So okay, we are classifying it as original model, instruct fine-tuned model, and PEFT fine-tuned model to compare later on. So your original model is the original LLM that was available in Hugging Face, and it is just called as the original model. So we are doing a zero-shot inference over here, where you just create a prompt and you have your original model, and you pass in the input and you try to generate the output. So if when you use your original model, there is a conversation that is happening between two people where they want to try to upgrade their person. One is trying to tell person to upgrade a lot of things on his computer, like upgrade your CD. Do you have something, and try to upgrade it and all of those things. So the baseline summary is the human generated summary, which we will be comparing it with to calculate the root score all the time. So the baseline summary is person 1 teaches person 2 on how to upgrade software and hardware in person 2's system is the baseline summary that is a human generated summary. And with zero shot, your original model, without any fine tuning, without any PEF tuning, and without one shot or multi-shot inference, it is just telling that I'm thinking of upgrading my computer. This is the original model that we have. And when you are looking at full fine tuning, so for full fine tuning, as I told, full fine tuning, you will have to create a supervised learning data set. So supervised learning data set will be input plus output. And if you are doing full fine tuning on multiple tasks or instruction fine tuning, you will also have to give the instruction. So over here, the prompt itself will have the instruction as well on what has to be done. So you're telling the instruction explicitly as summarize, and then you are giving input and the output. So all of these things you are adding to the prompt. So that is why this is called as instruction fine tuning. So maybe you will pick 100 examples like this, and after picking 100 examples, maybe you want to do sentiment analysis, then you will change the instruction. You will say sentiment analysis, and then you'll give input and output. So something like that. And once all of you have created your data set like that, you will just tokenize it, and we are just seeing what is the shape of training, testing, and validation over here. I think for compute purposes, a low number was chosen, but higher numbers can be chosen as well. And now we are full fine tuning. So when we are full fine tuning, here are some of the training arguments that have been used. And the trainer is the API or the function that is available from Hugging Face. You give your original model, you give your training parameters that was defined over here, you give your data, test data and validation data, and you fine tune it. And after fine tuning it, yeah, you will get your instruct model. So no, this is just loading from there. And once that is fine tuned, you will try to print the output. So you have your baseline human summary, your original model's output, and your instruct model's output. So your baseline summary was person 1 teaches person 2 on how to upgrade software. And we saw the original model. It was not that great. And instruct model is slightly better. But then we will not be able to make out a lot from this. So what we are trying to do is we are trying to use the Rouge score. So there is this library called as evaluate, from which you will get the Rouge score to calculate the Rouge score. So this is just for a couple of examples. It's printing what is the human baseline summary, your original model's baseline summary without zero shot inference, without fine tuning. And this is instruction fine tuned baseline summary. We can read this, but it's not going to make a lot of sense to us as of now. We will need to evaluate it using scores, and here are the scores. So your original model has a Rouge 1 score of 0.24, but your instruct model has a score of 0.41. So you can see that when you fine-tune it, instruct fine-tune it, the score improves. And Rouge 2 is over here, and Rouge L is over here. I'll pause here for a few minutes. If you have any questions, please ask.
Shubha, hello.
Yes, please go ahead.
Good morning, Shubha. Very wonderful presentation. One thing I wanted to just ask, maybe you're going to cover it later. I have been working in LLM and RAG for some time, and there are some drifts that are happening, right? When we create the fine tuning, and we all know in machine learning that we have to how we take care of drifts, right? With the recency stuff. So what is your experience? Maybe you will cover it later, or maybe it is out of scope, but you have had any experience in that? Like, because the quality of the output reduces, and we need to, and because what's happening that if you want to retrain the data and do fine tuning every time, it is also, as someone was asking, that Ashutosh, it is cost computing also goes up. So how to balance this for quality, accuracy, and also for production level cost optimization?
I have personally not done this. Do anyone else want to pick up this question? In case you have experience in doing this on your PVs or projects.
And just one more thing before someone, this particular thing that you have ran, this is on local, right?
No, SageMaker. No, it is on the ML 2x large of SageMaker.
And the cost for you to do this particular...
I have downloaded the file from SageMaker.
Okay, so not much of computing, that it is mostly for the instance. And
yes, for the instance was M5 2x large system. So it is slightly more than the basic things. I do not remember the exact vCPU and RAM, but it is slightly higher. So yeah, on SageMaker.
Thank you.
Sure. Anyone has an answer to the question that was just asked? I'm sorry that I couldn't answer it.
Yeah, maybe we can take it offline. This is something that I personally am looking at as well. Thank you, Shubha. Thank you for your time.
Please do post. Sure, no problem. Please do post on the group. Probably people who are not on the webinar might have answers and they might help you out. Okay, so here are the results for the original model and the instruct model. And this is again, sorry.
Just one more question. This is Jen. I'm not familiar with the terminologies used for models in LLM. I'm more of a machine learning space guy. Would you compare a Rouge 1 score to like an F1 score that we used to, we still use in the machine learning environment?
So so I believe you joined a bit late because I had a slide for the same. So I will just go through this quickly.
Okay. Thank you.
No problem. So I hope you're familiar with unigrams, bigrams, and n-grams. So unigram is just a word that you have in your text. Bigrams will be set of 2 words that you have in your text, and n-grams will be set of n words that you have in your text. So here is a reference that you have. Reference that is the human is just a reference or a baseline that you're trying to say that it is cold outside, and your model generates an output, it is very cold outside. So how do you compare these two things? So the formula for that is how many unigrams are matching. It is cold outside, all of the 4 things are matching. It is cold outside, all of the 4 words are matching, and how many unigrams are there in the reference. So in the reference there are 4, so your Rouge score is going to be 1. This is called as Rouge 1 recall. And similarly, you have the formula for Rouge 1 precision. unigram matches unigrams in output, and that will be your Rouge 1 score for precision, and F1 is harmonic mean of precision and recall, and this will be your score. So this is Rouge 1, where we are considering unigram. You can calculate Rouge 2, where you will use bigrams, and you can calculate Rouge N, where you use n-grams. And there is what is called as Rouge L, where Rouge L is your longest common subsequence. So in the reference baseline sentence and in the output that was generated, what is the longest common subsequence? Here, ETs is also a subsequence and cold outside is also subsequence with the same length. So both of them obviously will be the longest common subsequence. And then the count will be 2. So we will use, this is the formula, divided by unigrams and reference, and we will get a 0.5. There are slightly more other different small variations in the Rouge score, but at a high level, this is the formula that is available for Rouge.
So thank you. That's very helpful. Thanks for doing the recap.
No problem.
And you were reporting the Rouge 1 score in this code. Is that the F1 part of the Rouge 1 score, or is it the precision?
I think it's the F1.
And would you say, given the numbers that you're seeing, even with the instruct model, would you say that that is a reflection of your training data set? Or because 0.42, for practical purposes is a very low score, right? And I'm just trying to see, if we had to improve that, would you increase the size of the data set, or what other approaches would you?
There are some, size of the data set is one thing that matters. There are some hyperparameters as well. Yeah, here the hyperparameters for full fine tuning were set. You can play around with the hyperparameters as well to get better scores. So or you can also try out different models. Flantify model is used over here. Maybe you want to try out different models, try different hyperparameters as well, and also increase the volume of your training data set. So just like any other machine learning algorithm, kind of feature engineering and hyperparameter tuning and trying out different models like either random forest regressor or XGBoost regressor, whatever. So all of those things are something that you have to play around.
Okay, thank you.
No problem.
But isn't it the blue score when we look at the precision?
The blue score is generally used for translation jobs. Like if you are doing a language translation, and Rouge is generally used for summarization. But then, due to the formula, that is how is what it works. You can also print Rouge scores and also see how it works. Blue scores and also see how it works. So just like our normal machine learning, it will just be, the API will just be there in one of the libraries. You'll have to just Google and get the API and print it. So as I told over here, there is Evaluate. Evaluate was the library that we have installed, and Evaluate is the library that we've installed, and we are just getting it from Evaluate, the Rouge score. Okay, and here they have shown a percentage improvement of the instruct model over the original model. So full fine tuning of the instruct model over the original model, and the percentage improvement is something that's being specified over here. Moving on to PEFT. So PEFT is actually, as I told, for most of the things, the libraries are available, and writing code will not be that difficult, but then hyperparameter tuning and looking into those things are the things that will take time. So you have your PEFT library, and you can import your LORA config, and you have the get PEFT model. So what you have to do is, you specify the LORA config over here. Few configurations are available, and the rank over here is specified as 32, which is kind of a bit high. You can specify lower ranks and really try out how it works. So you specify the LORA configuration, and after you specify the LORA configuration, you use this getPEFT model. The getPEFT model will apply the LORA configuration to the original model. If you remember what was the original model was what we downloaded from Hugging Face, the FLAN T5 model. Whatever we downloaded from Hugging Face was our original model. Previously, we fine-tuned it using instructions and called it as the instruct model. We are still using the original model and applying the LORA configuration over here to get the getPEFT model. I think there was a question previously over here a few minutes back that how do we decide what are the parameters that will be trained? Do we decide or does the algorithm decide? So it is that you just specify the configuration and the algorithm will decide what are the set of weights that have to be frozen based on the rank that you have given and what are the set of weights that will be fine-tuned. So this algorithm internally will be using some approach, something similar to SVD, where you will try to find out the rank decomposition matrices, where you are trying to get the matrix which have the most essence. And that is all that you have to do. You just get the, yeah.
So what is target module here? Like QV?
I have to see, I'm not very sure. There are other hyperparameters that have to be tuned. So rank is the only hyperparameter that I went through. I can probably go through that. And yeah, similar to your original Hugging Face code that we saw earlier, you just specify your training arguments and you create a trainer and you train. And once the training has completed, what we are interested in, first we are interested in trying to understand how many parameters were trained. So this was your original model, and why is it 0? Oh, I'm sorry, I think it was around, I'm not sure. It was around 1.5 or 1.8%. So I'm really sorry about this. Probably I'll have to go back to my SageMaker and try to rerun this model. So this is around 1.8 or some such kind of percentage, 1.8 or 1.6 kind of percentage. So this is all of your model, and the percentage of trainable model from okay, yeah, it's here. Sorry, I was looking at the wrong side. I'm sorry, here you go. So yeah, trainable model parameters using PEFT is this, and all of your model parameters was this, and it is around 1.41%. So this is what we are more interested in, because now we will be looking at the root scores to see how good the accuracy of the instruct fine-tune model is. But at the same time, we need to also understand on how much of compute and memory we saved. So by looking at the number of trainable parameter modules, the total weights that you had was somewhere around this, and these are the trainable model parameters that you have. And that is the percentage. And so when I just scroll down and try to evaluate this using the evaluate module to find out the root scores. So yeah, the original human baseline summary is given, and how did the original model perform, how did the instruct model perform, and how did the PEFT model perform. We can read all of these things, but we will be more interested in a numeric value comparison of the summaries. So the summary is also listed over here on what was the baseline summary, original summary, instruct and PEFT model summary. Let's go down to the scores. And here are some of the scores. So the original model gave us something like 0.21. And the instruct fine-tune model gave us something like 0.41, and the PEFT model is giving us 0.37. So what you can see over here is it is a huge increase from 0.21, but though it is a slight degradation compared to your instruct model. But if you look at the number of parameters that you fine-tuned, it was just 1.41% of your total set of parameters. So as I told before, this is kind of a trade-off between this small accuracy increase and the huge compute that you are trying to save. So this was kind of a quick code walkthrough on what I wanted to show today. So if you have any questions, please do ask. I'll try to answer as much as possible, but then I have also been learning, so sometimes I might not be able to answer. Pardon me for that.
So Shubha, this Flan T5, you have downloaded the LLM. It's originally Google LLM, I believe.
Yes.
So we could easily replace this with a Llama 2, right, or Falcon or Mistral LLM by downloading it, right?
Yes.
Okay. So good presentation. First time I saw how details on PEFT. Folks, feel free to ask further questions.
Yeah. So one thing, Shubha, I wanted to ask: can we replicate this in Google Colab or our Jupyter notebook in local? If you download a small model.
Yeah, the small model you can probably, but I'm not very sure on the instruction fine tuning. You should surely try the PEFT fine tuning part of it. I'm not very sure on the instruction fine tuning. It is having huge number of parameters, and you might get that out of RAM or out of space error. But the PEFT model, you should definitely try it out.
Why I'm asking this, because very bad experience. But I'm not using AWS SageMaker for production. I'm using it for learning. And the bills, like if you need to be a little bit. You need to be a little bit variant, because when you use it as a beginner or your bills rack up, right? And then I stopped using a SageMaker for this reason. Maybe I have to, but I have to learn. There are ways that, like as you are doing, right? We can optimize it in a better way.
Yes. The other thing is, sometimes if you attend some of the AWS webinars, at the end of the webinar, they will try to give you some credit, AWS credit, something like $50, $25, something like that. So you can look at what interests you, some topics, and try to attend their webinars. At the end of the webinar, for all of the participants, they'll try to give some such credits. So a couple of times I have got this, and I have added it to my own AWS account, so that you can try something slightly bigger and not be charged for it. So that is also something that you can try out in case you make mistakes.
Subha, where can we get this code? Like, is it available on public or?
So no, this is not available on public. This was from deeplearning.ai that I picked up, and I executed it on SageMaker. But for educational purposes, it can be shared.
So deeplearning.ai, that website, you have downloaded this code, right?
It is not downloadable. There is generative AI, so I had enrolled and I got it from there. This code is fine, I can share, but then I have not run it on this local. I have just downloaded it and I'm sharing it with you. For reference purposes, you can definitely use and probably try to replicate at least the PEFT part on Google Colab or your local.
Yeah. Fine. Yeah, thank you.
Shubha, this was a great presentation, really informative. So thank you for giving that. My question is on the practicality here, and then I want to come back to your the outcomes, the score you got. If this is a small to mid-sized business, naturally data is going to be a challenge. If with 12,000 I forget if it was 12,000 summaries that was used to get a score of 0.41 or 0.42. That's a fairly large data set in-house to use just to get the training exercise done. If the only way that accuracy can improve is, or one of the best ways to improve accuracy is a larger data set or maybe some other approaches, What is the feasibility of using this in a, let's say even a mid-sized company, where internal data will be a key limitation? So in effect, is this only workable for very large size enterprises which have, massive amounts of data?
So the trade-offs that, okay, I will share my perspective as well as, and once that is done, if any of you want to share your perspective, you can go ahead. So the trade-offs will be, you can try bigger models if you are not having a huge amount of data, and try to tune some of the hyperparameters. This was like for a very few number of epochs as well as very few number of steps. So those are some of the things that can be increased. And if you are trying to do for a particular task, you can try out different LLMs. So this there are LLMs that are specific or can do better on some particular tasks. So if you're like talking about summarization, you can probably choose a better model which has been pre-trained to do better on summarization, and then more than a generic model. So those are some of the key things that you can try from what I have learned and my experience. If others have experienced something different or you have additional thoughts, please do share.
Just to add to that, Shubha. So see, this is from the research point which we found out. Nothing, we haven't tried it yet. So if we look into the LIMA paper, LIMA, so what they have mentioned, even if you have like less than 100 samples, it's more than enough, as long as the data quality is good. So they have tried it in 50 samples, if I'm not wrong. And with just 50 samples, they were able to achieve a very good accurate model, the fine-tuned model. And even if we go into the OpenAI, right, like a GPT-4 or GPT 3.5 fine-tuning, in one of the blog they have mentioned, you just give us 10 samples, it's more than enough. The GPT-4 model can pick it up and answer your questions. So as long as the data quality is good, I think we can get a better output. But what I'm not sure is, as rightly pointed out by Shiva, what is the which kind of a model? Is it a large model or a small model? For a small model, will 50 samples will suffice or 100 samples will suffice? That nobody is talking about now. Maybe in future we will see some more research work is happening there.
Correct. So yes, that is another key thing. Like if you do not have a lot of data, if you can at least try to improve the quality of data, that will for sure have significant results.
Yeah, with large LLMs such as Llama 2 or GPT, few shot prompting or few shot fine-tuning could give good results. Because the large language model has extremely powerful language understanding. So so even with few shot prompting, it might give decent results, but it has to be tried. But Flan T5 is a slightly older LLM, a smaller model compared to the state of the art, which is GPT-4 or Llama 2. So it may need more data for better fine-tuning results.
Also, one question on let's say these metrics like ROOG and Blue, they probably kind of test on if there is an exact match word. So if the word is like exactly matching with the ground truth, then it gives the score. But it's possible that let's say the output is kind of having the same meaning as the ground truth, but the words are not matching. So the score will be less. So are there like some other matrices which are like more semantic based, like scoring instead of just matching the words?
I have to again see that, but generally these are so there were a few other scores that the OpenAI. Let me just share my screen. Give me 1 minute. Though I am not aware, on the PPT on the paper it was there. So So some other scores were also used for some of the, apart from blue and rouge, this was on the paper. This is on the paper of, though I'm not fully familiar with what are the other evaluation metrics that they are trying to cite over here.
Okay.
Other things are available which we can probably explore, but as you said, yes, something more semantic wise will be more. If you are not using the same word, you might not be using, especially summary, if you're not using the same word, something similar will definitely try to help. But yeah, so something around that can be explored as well. Other evaluation metrics.
Maybe we can look into some distance metrics like cosine similarity, or these are not foolproof, but directionally they can provide direction values.
Correct.
Okay, so thank you all. In interest of time, so any final quick comments or questions, anybody, before we close the webinar?
Yeah, I just had a small doubt. So maybe Shubha, if you can just talk a bit about how the training data looks for the pre-trained model. So for example, it might have been trained on multiple tasks. So let's say for in case of summarization, we have like sequence of words as input and sequence of words as output. But for let's say for the sentiment analysis, we have only single word as output. So do we just combine all of these training points and feed it in one transformer? Like, how does it actually work?
You are talking about instruction fine-tuning and PEF fine-tuning?
No, for the pre-trained model. Let's say for training the pre-trained model.
Yeah,
Like,
so that will be fine-tuning. So you have your pre-trained model and you're trying to fine-tune it on top of that. So so yeah, see, like the prompt that you create. So this is, you are trying to create a, we are trying to create an instruction specified data set. So when you're trying to create an instruction specified data set, you explicitly give the instruction, summarize the following conversation and whatever is the dialogue. You say summarize this dialogue and that will be your input. So if you're trying to do it, and this is the data that will be used for training. So, and this was also the data that was used even in your PEF model. So if you're trying to do it for some other task, you will have to give a proper instruction for instruction fine-tuning is what I'm telling, and then specify what, specify the dialogue. So this dialogue itself will have both. It will have the X and Y. So this is the X, see, summary, and summary will also be there. So you will have to create your input data set in that way with the correct instruction. And once you do that, you can feed it your model for both instruction fine-tuning as well as PEF fine-tuning.
Okay, so for like let's say for the pre-trained model, like they are also trained in a similar way, like how fine-tuning is done.
Pre-trained will not be, no, pre-trained is done by all those big people. So it is, they do it on huge data sets that is publicly available on various tasks, but kind of, yes.
But output for them is like whole sentence, right? I mean, like sequence of words and not just the next word.
Sometimes it will be human generated and sometimes, so sometimes it will be human generated. So anyone wants to talk about how the original models themselves are pre-trained? Something like how was the original training itself done and not the fine-tuning?
There were a lot of labelers involved, right? If you read the paper, it was not an easy task, right? When I have gone through the papers and in details, we are looking at something that is being created by 6 years of work by OpenAI and Google. Everything has been, there were 10,000 or 100,000 labelers that were involved in making sure that the output is done accordingly. This is what I have read from the papers and what I've talked to some of the OpenAI people who have worked with OpenAI.
Yeah, but how the training data looks? I mean, is it like, so are they predicting only the next word, or is it the whole sentence they are predicting? Like what they give as the output for the pre-trained model?
No, it is the next word. For the most part, it is next word prediction. So that's pretty much traditional natural language understanding and prediction. So it is probabilistic modeling. So our core, at the very core, it is predicting the next word. And even in a sentence completion, that's how it does. It is trained on LORA dataset. Most of these large LLMs. So LORA is one of the most popular internet scale datasets, from what I understand. And it is able to, because of the massive data set, it has learned the common language understanding, and that creates a foundational model for downstream tasks.
Okay.
So it's been a while, so we like to close this. Thank you very much, Shubha. Excellent presentation. Thank you, audience, for joining, and look forward to future sessions from Shubha. She is one of our top AI researchers in self-chat community.
Thanks, Vivek.